The question says that there is a current carrying wire. So the current, let's say it's I. They're saying there is a wire loop. So the wire loop is square wire loop. So let's say they said that the length is L. They said the distance here is A. They're asking you to find the magnetic flux to this square. You have to understand the important point to understand here is the magnetic flux, magnetic field is like this, which means it's going into the paper over here. Let's assume that its current is this way, so that means the magnetic flux is here. But the issue here is magnetic field is not constant. So you see, magnetic field is high here, and as you come here, the magnetic field will be decreasing. So that means it's a varying magnetic field. So if you recognize this, you will understand that the importance of this problem is it's not direct phi is equal to B dot A, which is a easy one. This is true when the area and magnetic field are constant, but the area is constant here, but the magnetic field is dropping, because of the distance, because you know that it is magnetic field due to a wire is equal to mu naught by 4 pi to I by R. Okay, so that means since the R distance is changing from this point, magnetic field will also be changing. So that means suppose if I consider a small, so all I have to do is consider a small region like what we do in our differentiation integration. So take a small region and we are going to call this location, we're going to call it as X. So that means the small magnetic flux in this region, small magnetic flux d phi is equal to d dot dA. Let's ignore the cos thing because it will be cos 0, because the area vector on the magnetic field will be 0 degrees or 180 degrees. So this will become, let's take it as cos 0, so it will become 1. I want this location, so that means I'm going to write as X. dA is area of this small strip, right? So this small strip, which means this is also L square loop. So this is L, this is also L. So that means L into dx is the area. So that means if I want the total magnetic flux, I just have to integrate this. It means integrate this mu naught by 4 pi is a constant, current is constant, L is a constant, length of the wire loop. So only the x is going to change from here to here. So it's going to change from x is equal to a to x is equal to a plus L. So let's call this location as x is equal to a, and this location as x is equal to a plus L. That means I'll be writing this as dx by x integration x is equal to a, x is equal to a plus L. So that means I'll be getting mu naught by 4 pi to IL. So integrate this. So integral of 1 by x is log x. So log or ln x. So log x. Apply the limits a to a plus L. Log, sorry, this will become a log a minus log a plus L. Then I can rewrite this or simplify this as mu naught by 4 pi. Generally, I don't like to cancel this because mu naught by 4 pi is a constant 10 power minus 7. So I like to keep it separately. So you can simplify this log a divided by a plus L. Because you know that log m minus log n can be written as log m divided by. So that's the solution. So I would say this black part is all just mathematics. So the first formulation part is very important. So you have to understand that the magnetic field is not constant, it is changing because of the distance. If you recognize that, then it becomes an easy problem. So you just have to formulate the problem with the calculus basics. So I have been documenting website guruacademyandlabs.blogspot.com. So you can send me the doubts. If you have any doubts, I can try to answer it. Thank you.